I thought this problem was gonna be more difficult than what it was. It was actually a relatively simple problem. It says determine the reactions at A and B, right? When beta is equal to 30 degrees. So it gave us this, right? 30 degrees. And while we're at it, this is 150, right? That's 30 degrees, so it's sine of 30. And this is 150 newtons. Cosine of 30. And my free body diagram, I'm going to replace the wall, right, with a force A or AX acting perpendicular, right, to the plane. And this is a pin connection, so it's got dy and a dx. And I just put them all in positive, and then we see what happens, right? We get a solution in negative, we know the sense is the opposite. And the magnitude should be correct, assuming we did the math right? So, in a state of equilibrium, right, we would use the sum of the forces of x and y, and the sum of the moments is equal to 0. And I would start by summing the moments at this point right here. Sum of the moments at D, it knocks out dx and dy, and I'm left with just one unknown force, right? And its moment. So, summing the moments at D equal to 0. 0 is equal to A times its perpendicular distance for its moment arm, 180 millimeters, and that's generating a negative moment, isn't it, with respect to D. And then I take the two component forces here at 150. At 150 sine of 30 at 100 millimeters. 150 sine of 30, and its moment arm is 100 millimeters, and that's generating a positive moment, right, with respect to D. Plus 150 cosine of 30. And its moment arm, 280 millimeters, and that's generating another positive moment. So for A, right? We got for A, A is equal to 243.74. A is equal to 243.74 newtons, right? The millimeters drops out, which is basically 244 newtons, and it was a positive answer, right? And we had assumed it was positive, so indeed that is the answer for the reaction at A. So far so good? Now to get the reactions at D, the dx and dy, it's component force reactions first. All we have to do is sum the forces in x and y. Sum of the forces of x is equal to 0. 0 is equal to, well, dx we said is positive, right? We have 150 sine of 30, also positive. And then we have 243.74, the reaction at A, which is also positive, right? So that tells me what? Dx is going to be a negative answer, right? So I solve for dx, and I get dx is equal to negative 318.74 newtons, or sense of the forces acting in that direction. And then I go ahead and I look at the sum of the forces of y, set it equal to 0, and I've got dy, which I also set as positive, right? And then I take the 150 cosine of 30 negative. 150 cosine of 30 negative, and dy is a positive answer. And we should get 129.9 newtons acting out, right? Because it was positive. So, to find the reaction at D, I could just plot out those forces, right? We got negative 318.74 newtons, and positive, probably should have put that on the bottom. Let's move that over here. Negative 318.74 newtons, and positive, that is 30, right? 129.9 newtons. So D is gonna look like this. Right? Pythagorean theorem, D is equal to the square root of the sum of the squares of its components. Negative 318.74 newtons squared plus 129.9 newtons squared. And D winds up being equal to 344 newtons when I put in 3 significant digits. At a line of action in sense that looks like that, right? At a direction of tangent of theta x is equal to opposite positive 129.9 newtons over negative 318.74 newtons. The newtons drop out. Don't forget the negative sign, and theta x is like on 22.2. 22.2 degrees. At 22.2 degrees. And that's the reaction at D. What do you think? Make sense? Those two are easy, right? I thought this one was gonna be a little bit more challenging, but it wasn't. That's fine. No questions? Anybody need to get a photo or anything, find a photo?